Thank you for the introduction. Just a short introduction for those who don't know yet another coupler. It started as a research project together with René Redler from the Max Planck Institute. And we took the what we thought were nice ideas from ICON-ESM and kept developing into and played around with it a little bit, which resulted in YAC-1 being released in mid-2014. The overall concept of the user interface is very similar to OASIS as it is now, because we came from the same base, basically. It has online parallel weight generation in 2D, and by now there are various different interpolation methods like nearest neighbor with different weighting options, patch recovery as seen in ESMF, also conservative in first and second order. And the second order in this case is the same, or is based on the same paper as in ESMF and XML, XRS as far as I know. I had some problems with patch recovery with the results. Therefore, I looked into a little bit of a alternative, which resulted in the hybrid cubic spherical Bernstein-Bizet patch interpolation. Difficult name. Maybe this is of interest to other people as well. YAC introduced the interpolation stack concept, which is used when a interpolation fails for a target point or target cell. Then the user can select any of the available interpolation methods as a fallback. And to make it more general, we don't limit the number of fallbacks at all. So the user can provide a whole interpolation stack of different methods until all points or cells are interpolated or the stack is complete. YAC explicitly supports cell edges on grade and latitude circles, which we see later why that is. About a year ago, I started to rewrite everything internal, the internals of YAC, because I had a new idea on how that might work, and because YAC-1 was really sometimes quite complex, which made it hard to maintain, and writing new methods interpolation method was quite complex. The main idea of YAC-2 is that it internally has its own decomposition, which has two unique properties. One being that each process is responsible, or each process, source, or target is responsible for a unique area on the globe. And the second property is that the number of source and target cells within this area is similar across all processes. The result is that if you want to compute the interpolation weights, you nearly have all data already available on each process, and you only need to do a little bit of communication around the edges. That makes it quite quick. I expect YAC-2 to be a first version of YAC-2 to be released at the end of 2020. This is on some technical issues. We've seen before that script has a couple of problems close to the pole. One of the problems is that it doesn't explicitly support latitude circle cell edges. And here you see one of the reasons, because if you see a Gaussian cell that is close to the pole, then when you look directly down from the pole, it actually looks like the left example. And if you do not support latitude circle cell edges, you see the example on the right. And as you can see, if you compute the overlap between the two, the results look quite different. And in the left example, you see that the Gaussian cell is concave, which is for some clipping algorithms that are used to compute the overlap between two polygons a problem. Therefore, we use the Sutherland-Hodgman algorithm, which works quite well in that case. Imagine if you have defined a grid in a global domain where the grid is the blue stuff on the left, and if you want to partition that into 8 equally sized pieces, one method of doing that is a simple bisection algorithm where you recursively divide part of the grid into equally sized pieces, or you cut it into equally sized pieces where each cut is a straight line, and each cut is orthogonal to the previous cut, and the cut goes through the centroid. Such a cutting structure can easily be stored in this tree where each cut is represented by a 2D coordinate. Unfortunately, this explicit algorithm doesn't work so well on the sphere. That's why we modified it slightly and call that sphere part. The major difference is that instead of straight lines, we use great circles, and we can still store that in a tree structure. But now we store 3D norm coordinates of the planes that go through the great circles. Why that is important, we see on the next slide. Because the sphere part algorithm is used quite heavily in YAC, majorly to generate the internal decomposition. And since this cuttings tree is so easy to store or consume so less memory, each process can store this cutting tree, which results in the whole thing being a distributed directory for grid data, because each process can locally compute which other process to ask for data if it needs data on a certain region, in a certain region. In addition, we use this algorithm also to speed up on each process locally the weight computation. For example, on the local data, we put all local data into such a tree, and then can easily find candidates for the nearest neighbor search. Or, for example, if you want to compute conservative and you want to limit the number of overlap computations you want to do, you can use this tree and to pre-select cells that might work quite well. I did some performance measurements on a system that we have locally that has 2 Xeon Hasbro processes per node. I had to use an old version of MPI, of OpenMPI, because all other versions or MPI implementations are either too slow, too buggy in respect to MPI data types, which I use quite heavily, or don't work on our system. My test configuration consisted of 24 processes per node, and I used a toy model with 2 models, one using a global cube sphere grid and the other in global icosahedral grid. I computed the weights for the interpolation in both directions, used different interpolation methods, and I measured the time it takes YAC to set up the whole coupling setup. This includes the weight computation. And then I also measured the average time for a data exchange in both directions. This shows the general initialization time for 2 different setups. One, the low resolution case using 1 million cube sphere cells and 250,000 icosahedral cells, and the other using 4 million cube sphere cells and 1.3 million for the icosahedral grid. The horizontal axis shows number of nodes per component. If you want to have processes, you have to multiply that by 24. As you can see, the initialization time is, from my perspective, reasonable across the whole bound. And with increasing processor counts, the resolution, grid resolution doesn't matter anymore so much, because the communication is the limiting factor. I also tested for the high resolution test case different interpolation methods, and as you can see, conservative is obviously a lot more costly, but I think initialization time is still quite low. This is exchange time for both resolutions, and that scales quite well across the whole range. Okay, I also did some very high resolution test cases with a cube sphere with 4 million cells and an icosahedral grid with 335 million cells. With less than 8 processes, it didn't work due to memory constraints. But for more processes, you see that scales quite well and is within reasonable bounds for this grid resolution for both the initialization and the exchange, I think. Just to sum it up, some key points. We have a parallel on a weight computation, which is quite quick from my perspective. The main user currently, or more or less only user, except for one other user, is the ICON-ESM model. It uses YAC1, which will most probably be replaced with YAC2 at some point. The hybrid cubic spherical Bernstein-Bezier patch interpolation might be a potential replacement for patch recovery. Maybe you want to look into that if you have an issue with that. In case the interpolation stack concept, if it's interesting to other users, maybe other couplers might have a look at that. I think it's a nice concept. Just a couple of words on the ICON-Earth system model. There YAC is used to couple the ICON atmosphere and the ICON ocean, and the ICON ocean to the land model YAC. On the left, you see a typical setup where you have a low resolution atmosphere at the top and a higher resolution ocean at the bottom, where the ocean is missing all the land cells. The ICON-Earth system model comes in a variety of different configurations, from low resolution to very high resolution, like the diamond case, where you have a ICON atmosphere and ICON ocean with a 5-kilometer grid spacing globally, which is used for global storm and eddy resolving simulations. And on the next slide, we have a picture of that, where you see ocean currents and clouds. This visualization was done by a colleague. And that sums it up on the next slide, please. That's it from my side. Thanks for listening.